Good afternoon, class. In today's video, what I'd like to do is to talk about special relativity. And the whole reason behind special relativity, and the reason I want to talk about it, is because this is the part of the physics class that I think is the most fun, because now we get into the scientific or in the sci-fi realm of this class. And so today's the sci-fi popular culture term for today's video is time travel. We're actually going to talk about how to do time travel and break it down because it's a little bit more nuanced than you think. For example, you traveling to the future is very easy. Everyone can do it, and we actually have technology to do it today, right now. Traveling to the past, on the other hand, that's a different story. That requires much more futuristic technology than we currently have, but we're working on that. So what does that even mean to travel to the future? And in fact, how do you travel to the future in a way that with today's current technology, which can barely get us into space as it is? Here's how. And now for this one, we're going to take some cues from Albert Einstein and some of the ways that what we call thought experiments. And in this thought experiment, we're going to see how the laws of physics would apply to a very specific scenario. So in this case, we're going to start with this thing called a light clock. Now what this means is I basically got two mirrors over here, and they're drawn in black. The photon there's a photon that's going to bounce between the two mirrors that are a fixed distance away. So that blue line is for the photon to bounce amongst the mirrors, and that's what's going to happen from the perspective of somebody who's on, let's say, on a rocket ship, who's traveling with these two mirrors. So let's say this light clock is on a spaceship that's traveling in space. So what the person on the clock, the person, when they look at this clock, they see and they're on the rocket ship along with this clock, what they see is this motion, okay? If you're on Earth, however, you actually don't see this motion because this rocket is moving in this direction with a velocity v. And so what you would see is as the photon goes up and down, you would see it go up and down at this angle. And so, we can actually label all of these different perspectives from using a right triangle, because that's actually what this forms. If you hopefully notice that this right here is a right triangle. So now it's time to get into a little bit of math, and for this we're going to need to use Pythagorean's theorem, and hopefully you've either seen it before, but if you haven't, here it is: c squared is equal to a squared plus b squared. And so what we're going to do is we're going to define which one is which. So this is c is the hypotenuse. So in this case, it's going to be this side right here. This can be A, and this can be B. Okay. Now, one other note: this c right here is not the same as this c. This c is the speed of light. So when we write this out, we're only talking about this because the normal time frame or the normal distance that the light clock would be if the photon goes up and down. So we're only talking about the photon going up from one mirror to the other. So that distance, that's where these 1/2 factors come in. And so that's just something to keep in mind. Now, one of the things I did want to point out over here is there's this little prime over here, or this little tick mark right here, and there's none over here. The reason I did that was because I wanted to show that there was a different perspective, because if you're on the spaceship, you see the blue line. If you're on Earth, you would see this green line. Okay, so I wanted to show that there's a possible difference in the way time flows from these two different perspectives. Because one of the postulates that Einstein built all of special relativity and even general relativity on is that the speed of light is the fixed quantity in the universe. And because of that postulate, he built everything from there, and this is one of the consequences of it, which means that time actually can flow a little bit differently based on your perspective. So let's talk about how we get there. So using Pythagoras theorem, ct over 2, which is this one, that's our c squared. A is going to be ct prime over 2, and b is going to be vt over 2. Now, one of the things that I do want to notice, not only that, but we're squaring it, but also you see these over 2 portions, they're all the same. Every term has that something over 2. So what I did was, because I wanted to save some space for this video, is I did this without showing my work. But in this one, I just multiplied, because this is squared, I multiplied every term in this equation by a factor of 4. So doing that gets rid of the over 2 symbol, a fraction, so then I can just move on from there. So what I have is this. I've got c squared t squared equals c squared times t prime squared plus v squared t squared. So you're going to hear a lot of those squares in there, so bear with me. If it's hard to follow along based on what I'm saying, just follow along as I'm pointing it out on the board. So what I do now is I say, okay, well, I want to isolate, everything is a variable here, so it's not like I'm isolating only one variable to work with. What I'm going to do now is I'm going to isolate the different times just to see the relationship, because that's really what I'm looking for. I don't really care about solving for any one variable in particular. I care about solving, and for the simplifying the equation, isolating both sides of the equation, isolating each of the different variables so that I can see the relationship between the two. And in this case, time interests me, so I'm going to isolate t prime, and I'm going to put t on one side of the equation and t primed on the other side of the equation to see the relationship between them. So when I do that, I subtract v squared t squared from both sides of the equation, and again, I skipped a couple of steps, but I then, because t squared is the common factor between them, I factored it out and left them in a parentheses over here. So now I've got c squared minus v squared in parentheses times t squared equals c squared t prime squared. Now, I know that sounds like I'm saying c squared a whole lot, so what I'm going to do now is let's simplify everything a little bit, and we're going to divide both sides of the equation by c squared, and again, I didn't show that on the board because I'm still trying to save some space. So I divide both sides of the equation by c squared over c squared, as we did from our drills earlier this year, is 1. And then, so it's going to be 1 minus v squared over c squared. That's the result of this division here. So now I've got t prime by itself, which is nice. But really, I'm going to solve for t, so I'm going to just push everything to one side of the other equation, mostly because I prefer having the left side of the equation being solved for. Do I have to do it this way? No. I could do it any way I feel like, because even if I just solve for t primed over here, that would have worked as well. But in this case, I'm going to divide both sides of the equation by 1 minus v squared over c squared, so I get that. And then I'm going to square root both sides of the equation, because I don't really want to, because first of all, nobody knows what squared time looks like. Everyone experiences only time just by itself. Nobody has ever experienced a square second. So what I do is I'm going to take the square root of this whole equation. So I'm going to get t equals the square root of 1 over the square root of 1 minus v squared over c squared, all of that times t primed. Now, of course, this looks like a whole lot of work over here. So what I thought I did was put like the Cliff Notes version of this, which is, if you want to have time dilation, the time that you experience on Earth is the same as the time that I experience on the rocket ship, but simply modified by this factor called gamma. And what is gamma? Gamma equals 1 over the square root of 1 minus v squared over c squared. Now, one of the things I did want to do before I end this video, because I could just say, there's time dilation, but it doesn't help unless you actually have an idea of what this actually represents, because then you'll start to appreciate books like, for example, Ender's Game. That actually uses this equation quite a bit as a plot point in their story. So what this actually means is the faster you move, the more you move through space, the less you experience time. So the faster I move, the bigger the difference between this, which means that I could theoretically leave, travel fast enough, come back to Earth, and my children would be older than me. And if that seems kind of out there, that's actually one of the consequences of special relativity, and one of the ways that we can stretch physics out into the modern era. So it's something to think about, especially as we enter more of the sci-fi territory of the course. So good luck in your studies, and may the force be with you.